Today, class 26, we're going to talk about theorems about differentiable functions. There are three named theorems that we're going to discuss today: the mean value theorem, the increasing function theorem, and the racetrack principle. All right, so the mean value theorem says that if f is differentiable, which means it has to be continuous and it has to be smooth, that's sort of a layperson definition of differentiable, smooth and continuous, on an interval from a to b, then there is at least one number c between a and b, so that f prime of c equals f of b minus f of a over b minus a. So if we were to interpret this graphically, f prime of c, graphically, what is it? How could we draw that? What does it represent? A slope of a tangent line. Yeah. So this is the slope of a tangent line at some point c, right? Some x value c. How about f of b minus f of a over b minus a? What is that represented as graphically? That is the slope of what line? Close. It's a secant line. It's the line connecting a comma f of a to b comma f of b, right? So this is the slope of a secant line from a comma f of a to b comma f of b, right? That's just the formula for slope. y2 minus y1 over x2 minus x1. So here's my picture, right? The mean value theorem says that there is some tangent line that is parallel to the secant line. Where did this parallel thing come from? How do I know they have to be parallel? Because they have the same slope. Yeah, that's what it means for two lines to have the same slope. So we have a secant line that has some certain slope, and the mean value theorem says that there is at least one place, there's at least one x value between a and b, where the slope of the tangent line is the same as the slope of the secant line, meaning the two lines are parallel. So if I draw a secant line from a comma f of a to b comma f of b, put in a secant line here. I want to try to find some point, some x value between a and b, so that the tangent line at that point to the curve is parallel to that secant line. So that might happen here-ish. If I draw a tangent line there, parallel to my secant line, that is my special point C, an x value between a and b, so that the tangent line there is parallel to the secant line. So let's have a little graphical animation to make this as clear as we can. This one, okay. So here's some random function, f of x, and I've got an interval from a to b, and this function is smooth and continuous on that interval. So I'm going to show the secant line from a comma f of a to b comma f of b, this sort of teal blue color. So I am looking for a point, an x value between a and b, somewhere in this interval, that will make this tangent line at point P here parallel to the secant line. So I'm going to just have it animate here, and we go there, right, and there. So there's actually two. The mean value theorem guarantees that there's at least one. Sometimes there's more than one. In this case, there are two. Let's see, I'll slide this manually. Oh, look, I stopped it right at the parallel point. So, and then I can actually have this little program find C. So let's reset. Ooh. Show the secant. So find C. It just moves it until it hits this parallel point. And then there's another one, and it marks it C1 and C2, two different C's that make it true. Buy it? Mean value theorem? So the mean value theorem guarantees the existence of a special point on the graph of y equals the square root of x on the interval 0 to 4. What are the coordinates of this point? First, we have to verify that the mean value theorem applies, which means we have to ask ourselves, is that function smooth and continuous on the interval 0 to 4? Square root x. Is it continuous? Smooth? No jagged, sharp edges? Yeah, so we can use the mean value theorem. Okay, y equals square root x is smooth and continuous. So MVT applies. Okay, so that's the first thing you have to do. It only applies on a smooth continuous function. So the mean value theorem guarantees the existence of a special point in the interval 0 to 4. So if I'm looking at the interval 0 to 4, I can look at a secant line that connects the endpoints of the interval. So I would do slope of the secant. That would be y of 4 minus y of 0 over 4 minus 0. What's y of 4? 2. And y of 0 is 0, so this is 2 over 4, which is a half. So the slope of the secant line is a half. And I am looking for a point, an x value, where the slope of the tangent line is a half. Okay. So what mathematical object represents the slope of a tangent line? The derivative, yeah. So I'm going to take the derivative, which represents the slope of a tangent line, and what am I going to do with it? Set it equal to 1/2, yes. Because I want to know what x value, so I'm going to be solving for x, will give me a slope of a half. So I'm going to take the derivative. Y prime is going to be 1/2 x to the negative 1/2, or 1 over 2 square roots of x. And I want to set it equal to 1/2. Okay, because y prime is the slope of the tangent line. So I want to find out the x value that will make my y prime, the slope of the tangent line, 1/2. So I solve this thing for x. What does x have to be? 1. Yeah, that's the only thing it can be. So square root x has to be 1, which means that x is 1. Let's take a quick look at Geometers Sketchpad just to verify that this is the special point. Okay, here's square root x. I'm going to show the secant line from 0 to 4. And then here's my tangent line at point A. And I'm just going to drag this point until it looks like it's parallel to the secant line. And that should happen at x equals 1. Yeah. So right about here, the green line looks parallel to the red line. That happens at x equals 1, which is what we solved for algebraically. Make sense? All right. So the mean value theorem is a slightly intuitive result. Its proof is actually surprisingly difficult. And you can use it to find this special point, but mostly we use the mean value theorem to prove other important things. Okay, so for example, here's a theorem that we have been using for a while because it's fairly intuitive also. But we haven't proven it yet, and we're going to now have the mean value theorem to help us prove it. So the increasing function theorem. if f is a function that's differentiable, that is smooth and continuous, on an open interval a to b, then if f prime is positive for each x value in that interval, then f is increasing on that interval, right? F prime positive, f increasing. If f prime is negative, f is decreasing. And if f prime is 0, f is constant. So if we want to prove it using the mean value theorem, so when you're trying to write a proof, you should start by writing what you're given, right? What we already know, and what we need to show. Okay. So let's just prove part A here. In this sentence, what are we given and what do we need to show if you want to prove that that sentence is true? Yes, we are given that f prime is positive. Yeah, so we're given the if part. We have to prove the then part, right? So what do you need to show to prove that f is increasing? What does it take to show someone that f is increasing? How do you know when you look at a graph that f is increasing? As x increases, y increases. Okay, so I'm going to just take that sentence, make it a little bit fancier. I'm going to say that if x2 is bigger than x1, right? So you have some value of x that's bigger than another value of x, then how do f of x2 and f of x1 have to be related? F of x2 has to be larger. Perfect. As x gets bigger, f of x gets bigger. Does that make sense? So I just wrote it a little bit fancy so that we can use mean value theorem to prove it. All right, so I know that f prime is positive, and I need to show that this statement is true. I need to show that f of x2 is bigger than f of x1. All right, I need a new page here. So here's my interval a to b that they gave me, right? And I have picked, and x2 and x1 are completely random. If I can show that it's true for a random 2 points, then I can show that, then I can say it's true for every set of 2 points. So these are completely random. I'm just going to put an x2 and an x1 on my picture. For any x1 and x2 between a and b. x2 is bigger than x1, right? All right, so I need to show that f of x2 is bigger than f of x1, right? So that this is what I need to show, that f of x2 is bigger than f of x1. All right, so because I know that f is smooth and continuous, I know that the mean value theorem applies. So if I were to draw a secant line between those 2 points, then that would be f of x2 minus f of x1 over x2 minus x1. That's the slope of that secant line. And the mean value theorem guarantees that there is some number in between x1 and x2, so that the slope of the tangent line equals the slope of that secant line for x1 less than c less than x2. Okay. So there's some c in here that makes that statement true, just the mean value theorem. But what do you know about f prime of c on this interval? It's positive. That was the piece that I was given, right? That's the thing I can assume. F prime is positive on every point between a and b. Okay. So I know that this is positive. So I'm going to solve for f of x2 minus f of x1, and that is going to be f prime of c times x2 minus x1. All right, so f prime of c is positive. What's x2 minus x1? Positive, because we drew this so that x1, so x2 would be bigger. So this is positive. So what does that mean? F of x2 minus f of x1 has to be positive. Positive times a positive is a positive. All right, so if f of x2 minus f of x1 is positive, what does that tell you about the relationship between f of x2 and f of x1? F of x2 is larger. If you do a subtraction and you get a positive number, that first number had to be bigger. Or you can just think of it as adding f of x1 to both sides. F of x2 is bigger than f of x1. Again, I'm not really going to hold you responsible for being able to prove this theorem. You're mostly going to use this theorem. But as you saw in the last test, sometimes I like to have you prove things for bonus. So an interesting bonus question might have you prove that piece, right? We did the first one. You can follow the exact same model, do the second one. All right, so that's our second theorem of the day. We've got the mean value theorem. Just says that there is some place where the tangent line is parallel to the secant line. Then we've got the increasing function theorem. And finally, we have the racetrack principle. All right, suppose that g and h are two functions that are differentiable on an interval a to b. So that means they're smooth and continuous. And g prime is less than or equal to h prime always on that interval. G prime is always less than or equal to h prime. Okay, so if g of a equals h of a, so they have the same value at the beginning of that interval, what can you say about the y values of g of x and h of x on the entire interval? Less than, greater than, equal to. How are they related? Yeah, how do you know that? It's going to be increasing faster. Yeah, if the slope of h, because that's what h prime represents, right? The slope. If the slope of h is always bigger than the slope of g, that means that it's increasing faster than g is, right? So if they start at the same place and h is increasing faster, h is going to get bigger. H will always be bigger. And let's flip it around a little bit. Still, g prime is less than h prime, but now they're going to finish in the same place. So g of b equals h of b. They finish in the exact same place, but g prime was always smaller than h prime. How can you talk about the relationship between g and h in this one? G of x is bigger. Yeah, can you explain why? Mm-hmm. Yeah, you got it, exactly. Yeah, so if h has a greater slope, then it's increasing faster than g is, right? But if they finished at the same place, then g must have had a head start, right? So why do you think this is called the racetrack principle? Sure. Yeah. Think of if G and H are representing distance and time, right? If X is time and G of X and H of X are distance, and G of X and H of X are racing, then G prime and H prime tell you the speeds of the two racers, the velocities, right? Think about the zombie race that we talked about at the beginning of the semester. So if zombie 1 is slower than zombie 2, and they start at the exact same moment, right? They start at the exact same place at the start line. So they have they're tied at the beginning, and H is faster than G, then H will always be ahead of G, right? They start at the same place, and zombie H is running faster. Zombie H is always going to be ahead of zombie G. But then flip it. So now they tie, right? My two zombies tie. It's a photo finish. But H was running faster than G the whole time. It has to be that G had a head start. That's the only way they could tie and H be the faster zombie. So G had a head start, and G was ahead of or equal to zombie H the whole time. All right, so let's use this principle, the racetrack principle, to prove that sine of X is always less than or equal to X for all X's bigger than or equal to 0. Okay, so the racetrack principle. So let's have this be G of X and H of X, right? So I want to apply the racetrack principle. I can conclude that G of X is less than or equal to H of X if G of A equals H of A, right? And G prime is always less than or equal to H prime. So I need to show two things. I need to show that and that to conclude that. Okay, so that's what the theorem says. It says, suppose these things are all true, right? So we get to assume those. Those are given. And then you also get to assume the if part of an if-then statement, and you have to prove that the then part. All right, so let's see. We have G prime has to always be less than or equal to H prime, and G of A has to equal H of A. So 0 is going to be our A here, because that's the starting point of our interval. This is the interval 0 to infinity. Okay. All right, what is G prime? Cosine X. What is H prime? 1. Is that a true statement? Is cosine of X always less than or equal to 1? Yes. Okay. And what is G of 0? 0, yeah. And H of 0 is 0. True. So I've shown the two if parts are true. That means I am allowed to conclude the then part. Okay. So racetrack applies. I've satisfied all the given conditions. That means I can conclude the then. So racetrack applies, and it must be that sine X is less than or equal to X for all X's greater than or equal to 0. I don't know if you guys know this symbol. That means for all or for every. All right, so now there's a pretty extensive thing for you to work on here. I'll come around and help as needed.